Bioinformatics Micromodules, Maximum Likelihood for Phylogenetic Tree Reconstruction. In this module, we discuss some basic concepts behind maximum likelihood methods for phylogenetic tree reconstruction. The term likelihood in statistics has a specific meaning. It is the probability of the observed data given a model. In phylogenetic tree reconstruction, the observed data, which we use X to represent, is the set of input sequences. We assume that the sequences are already aligned and different sites are independent, such that we can focus on a single site in the following discussion. The model is parameterized by theta, such that when the value of theta is known, we can compute the likelihood according to the model. We will explain the parameters involved in phylogenetic tree reconstruction in a moment. The objective of maximum likelihood method is to find the value of the parameters such that the likelihood is maximized. Just like in maximum parsimony, we can define a harder problem called large parsimony and an easier problem called small parsimony. Here, we can also define different versions of the maximum likelihood problem, depending on the model parameters. In the big likelihood problem, the tree topology, mutation rates, and branch lengths are all considered as parameters of the model. Finding the optimal combination of parameter values is very difficult, not least because of the exponential number of possible tree topologies. In contrast, in the small likelihood problem, we assume that the tree topology is already given, and we only aim at maximizing the likelihood function based on different mutation rates and branch lengths. For this simplified problem, there are heuristic methods that usually produce optimal results, although, as in the case of all heuristic methods, optimality is not guaranteed. Here, we first study the subproblem of computing the likelihood with a fixed set of parameter values, assuming that the ancestral sequences are also known. For example, this figure shows a tree with 4 input sequences at the leaf nodes. The ancestral sequences at the 3 internal nodes are also given. If we are given the values of all 6 branch lengths and the mutation rates, how do we compute the likelihood? To compute the likelihood, we make use of the Markov property that the probability for the sequence of a node can be computed by the sequence of its parent node and the length of the branch between them. This property allows us to decompose the likelihood function into the product of several simpler terms. First, we need a prior probability for the root node to have nucleotide G. After that, we have 6 terms, respectively, for the 6 other nodes, each equal to the conditional probability of the sequence in the node given the parent and the distance between them. How do we compute these conditional probabilities? They can actually be computed based on a mutation model. For example, if we assume the Jukes-Cantor model, the mutation rate is a single parameter alpha, and all these conditional probabilities can be computed using the formula we derived in the last module. With this background, we can compute the likelihood of a tree when the ancestral sequences are unknown. In this case, we need to consider all possible sequences at these internal nodes. For the example shown, since there are 3 internal nodes, each with 4 possible nucleotides, we have 4 to the power 3, that is 64 combinations to consider. For each combination, we already know how the likelihood can be computed, and thus a brute force way to compute the overall likelihood is just to repeat this calculation 64 times and sum them up. If we analyze it more formally, we have 64 likelihood values to sum up, each of which involves the product of 7 terms. Both the values 64 and 7 depend on the number of input sequences, where 64 is 4 to the power of the number of internal nodes, and 7 is the total number of nodes, which is 2 times the number of input sequences minus 1. In general, if we have n input sequences, each with only 1 nucleotide, the brute force method requires the summation of 4 to the power n-1 terms, each of which involves the product of 2 n-1 terms. If n is large, this amount of calculation, which is exponential with respect to n, is impractical. Then how can we compute the overall likelihood efficiently? Thinking about the structure of this problem, you may realize that the brute force algorithm involves a lot of redundant calculations that we might be able to eliminate if we store the intermediate results properly. As you can imagine, we are going to use dynamic programming to compute the likelihood efficiently. Let's make an observation here, important for dynamic programming. Suppose we want to compute likelihood of a subtree. Once we have determined the sequence at the root node of this subtree, the likelihood calculation depends only on the parent of the root node of this subtree, but not any other nodes outside the subtree. For example, in the tree shown, if we want to compute the likelihood of the subtree rooted at node E, once we have decided that node E should take nucleotide A, the likelihood of this subtree can be readily computed regardless of the sequence at node F. This observation is important because the original problem can then be divided into subproblems that do not depend on each other. Now, let's study the algorithm in detail. As usual, in dynamic programming, we need to define the DP table. In this case, the DP table is called V with two parameters, I and X. Entry VIX is defined as the likelihood of the subtree rooted at node I when the parent of I takes nucleotide X. With this definition, we can see that the overall likelihood is simply the sum of 4 terms, corresponding to the 4 choices of the nucleotide at the root and the corresponding likelihoods of the left and right subtrees. This formula involves 8 DP entries, VEA, VEC, etc. Each of these entries can be computed by considering further subproblems. For example, VEA, which is the likelihood of the left subtree when node G takes nucleotide A, can be computed by considering all possible nucleotides at node E multiplied by the corresponding likelihoods of its own left and right subtrees. Finally, entries involving leaf nodes are simple conditional probabilities that can be computed directly based on a mutation model. The computation continues until all entries in the DP table have been computed, at which time the overall likelihood can be computed. How much time does it take to compute the overall likelihood using this algorithm? The number of entries in the DP table is equal to 4 times the number of nodes, which is linear with respect to the number of input sequences. Computing each entry of the DP table requires a constant amount of computation, assuming the conditional probabilities based on the mutation model can be computed in constant time. Therefore, the whole algorithm can be run in linear time with respect to the number of input sequences. Let's see an example of using this algorithm. Here, we have a tree with 3 leaf nodes. The root is assumed to have equal probability for each of the 4 nucleotides. We also assume the Jukes-Cantor model is used, with the mutation rate alpha set to 0.1, and each tree branch has a length of 1 time unit. We then define the DP table V as just described. Using the formulas discussed, the entries of the table can be computed. Finally, the overall likelihood for the whole tree can be computed based on the DP table entries. Now we have seen how the likelihood of the tree can be computed even when the sequences at the internal nodes are not known. However, the calculations still require the mutation rates and branch lengths to be given. How do we solve the small likelihood problem in which the values of these parameters are not known? Again, this is a searching problem, with the search space defined by these parameters. One method for solving this problem is hill climbing. We start with an initial guess of the parameter values, and then change the value of one parameter such that the likelihood is increased. to reach a new estimate of their parameters. This process is repeated until reaching a peak. Note that depending on the likelihood function, there may be more than one peak, in which case the hill climbing algorithm can only reach a local maximum. There are variations of this algorithm as well as other searching algorithms for overcoming this issue, but we will not go into the details here.